Welcome, ladies and gentlemen, to this second part of our lecture on emission-oriented transportation management. In this part, we will look at land-based and maritime transportation. We will have a brief look at road transportation and rail transportation, and then a somewhat more detailed look into maritime transportation. This first slide is dedicated to road transportation management. Road transportation is often treated as a so-called capacitated vehicle routing problem, which aims at determining optimal tours for delivering goods to a set of customers with respect to capacities of a vehicle fleet. In this small example here, you see 3 routes conducted by 3 trucks, and each of the trucks starts from some depot in node 0, visits some of the customers, and then returns to the depot. What decisions affect emissions in road transportation, respectively the capacitated vehicle routing problem? First of all, it is the assignment of customers to routes which determines the length that the vehicles have to travel. This corresponds with the visiting sequence. The second thing is the speed. But speed of vehicles can hardly be decided in road transportation because the trucks have to stick to the floating traffic. So this is of somewhat minor importance. An important decision is the choice of vehicles. What fuel do they use? What is the size of the vehicles? Is it small trucks? Is it large trucks? The second slide shows a corresponding example. Here we have a total of 15 customers that have to be served from the depot in node 0. On the left-hand side, we see a solution where only large trucks are available for the corresponding logistics company. In this solution, 2 trucks are needed because 1 truck is not sufficient for serving all the customers. In total, we have 2 routes here. Total fuel consumed is about 300 liters of diesel, and the total route length is 1052 kilometers. On the right-hand side, we see a solution that consists of 3 routes. In this example, the company has various sizes of trucks, large trucks, medium trucks, and small vans. You can see that one of the large trucks serves most of the customers, but 2 remote customers, 12 and 13, are served by medium trucks and vans, depending on the size of the shipment that they ordered. From this, we have a total fuel consumption that is reduced by about 10% compared to the solution on the left, because the smaller vehicles require less fuel, even though the total route length increases by 21%. This example shows you that a heterogeneous fleet can help reducing fuel consumption in land-based transportation. Slide 3 is dedicated to rail transportation. Rail transportation is usually conducted in the form of intermodal transport, where the movement of goods in one and the same loading unit uses various modes of transport successively without any handling of the goods during transfer between modes. We see this quite often if cargo is transported in containers. Container can be loaded onto a truck, the truck is sent to a rail terminal, it is transshipped onto the train goes to another terminal, is transshipped once more onto a second truck, and the second truck brings the cargo to the receiver. Compared to direct door-to-door transportation by trucks, we have several advantages of intermodal transportation. We reduce road traffic, we might reduce transport cost, and we potentially reduce emissions because trains are more fuel efficient with respect to the individual unit of cargo, and from this fuel efficiency we also have a reduction of the emissions. But there are also challenges of intermodal transportation. We have additional organizational effort because more parties are involved in intermodal transport. We have increased detouring and transshipment because we have to go to the terminals and load the cargo from the trucks to the trains and vice versa. And this might also affect an increased overall transport time. To achieve low emission rates on trains, cargo consolidation plays a major role in intermodal transportation. This is because a train has quite a large transport capacity, and the emission rate per transported container is low only if the train is fully loaded. Slide 4 visualizes this effect. It presents a graph that shows the emission rate measured in carbon dioxide equivalent per ton kilometer. So how much emissions do we cause from transporting 1 ton of cargo over 1 kilometer of distance? At the x-axis of this plot, we see the payload of the train in tons. The better the train is utilized, the lower the emissions per ton kilometer are, because we have some fixed emissions, for example, due to the dead weight of the train. In this plot, you see data that corresponds to 2 emission estimation models. The emission estimation model of Schmid and Knörr is quite rough. It does not capture the effect of the payload on the emission rate per ton kilometer precisely. The model of Kirstein and Meisel is somewhat more precise here. You see some spikes here. The spikes result from the need to add a further rail car to the train if you want to transport 1 more unit of cargo. So each time you attach an empty rail car, moving this empty rail car requires additional fuel. And if this empty rail car is not fully loaded, if it has just 1 ton of cargo on its back, we see this spike here. And then if the rail car is further loaded with additional units of cargo, the emission rate per ton kilometer decreases. Slide 5 brings us to the maritime transportation. In maritime transportation, we have different modes of transport. One is tramp shipping, the other one is liner shipping. Tramp shipping means that a shipper who wants to send an amount of cargo charters a ship, and this ship transports this cargo on demand. This mode of transportation is very typical for bulk cargo, such as oil, coal, or agricultural products or large items. Other types of goods, especially consumer products, are typically transported in containers on container ships. And container services are organized in so-called liner shipping, which means that the ship operators set up a regular scheduled transport service that visits a set of ports in a predefined sequence on a regular basis, for example once per week. What are relevant drivers of emissions in the maritime industry? Of course, the ship size. Larger ships can transport more cargo, but they also require more fuel. The payload, which affects the draft of a ship. The speed at which the ship goes, the weather conditions, and the type of fuel. Figure 6 shows us how fuel consumption depends on the ship's size and the chosen speed. We see that a higher speed affects a higher fuel consumption of a ship, and so does the larger ship size. Interestingly, in the maritime industry, choosing a speed for a ship is actually possible, contrasting road transportation where a truck has to stick to the floating traffic. For this reason, choosing a speed is actually an option to influence the fuel consumption rate and the emissions of a transport service. Slide 7 shows us that maritime transportation is also embedded into intermodal transport chains. This is because the cargo has to be brought from the shipper to a seaport and from a seaport to the final recipient, and for this we typically use trucks or trains or smaller ships like inland barges or feeder ships. For this reason, Intermodal transport chains in the maritime industry can be quite complex. In the following, we want to have a look at how to design container shipping liner services and what this means for the emissions that result from this transportation. A liner service basically defines a route of ports to be visited in a predetermined order and a service schedule such that regular service at each visited port takes place with a given frequency. In this picture, we see an example of such a liner service. The frequency is weekly, meaning that each of these ports should be visited once per week. There are 19 ports involved in this liner service. You see it's a round trip. You could say it starts in Hamburg, then goes through the Mediterranean Sea to India, and then back until it arrives in Hamburg again. The whole duration of such a round trip takes 56 days. Now comes an important aspect. If you want to visit these ports once per week, and if the round trip of one ship takes 56 days, we actually have to deploy 8 ships on this route in order to make sure that each of the ports can be visited weekly. You could think about this as follows. In the first week, one ship starts from Hamburg. This ship needs 8 weeks until it returns to Hamburg, which means that in the second week, we have to start a second ship from Hamburg. And in the third week, we have to start a third ship. The first ship that started from Hamburg can take the next cycle only after its return to Hamburg, which takes 8 weeks, and therefore 8 ships are involved in operating this liner service. At the bottom of the slide, you see management decisions that have to be made for setting up such a liner service. These decisions include which ports to actually service, what is the visiting orders of the ports, or the so-called routing of the ships, what is the size of ships that we deploy on the service, and what is the service frequency? Is it weekly? Is it bi-weekly? Further decision is the ship speed, and service frequency, route length and ship speed in combination determine the number of ships to deploy, because the three mentioned drivers determine the duration that it takes for one ship to travel the whole cycle. The mentioned decisions can be optimized through so-called vessel schedule design problems. The reference Dulubenis et al. 2017 presented such a vessel schedule design problem with an environmental perspective. Feel free to download this reference and go through the paper to see how mathematical optimization can be used for finding the appropriate decisions in such a complex problem. We will not go into details with the mathematical model here, but I will show you somewhat the complexity of such a problem by outlining the parameters, the data that goes into this problem. We need cost parameters, like the weekly operating cost of a ship, and the unit bunker cost expressed in US dollars per ton of the fuel that is used here. We also have inventory holding cost because there is a large amount of cargo on these ships that travels over the ocean, and throughout this time, this inventory causes inventory holding cost. The ships have to stick to their schedules, and there might be some arrival penalties if they are too late at a port. We have handling cost rates at a port, and we have emission factors for carbon dioxide, for sulfur dioxide, and for nitrogen oxide that reflect the environmental impact of the fuel that is used here. We have time windows given for the ports, and we have a minimum and a maximum speed for the ships. Within this range, we can choose at which speed the ships should go. All this data goes into the optimization of Dulubenis et al. 2017, and they can then produce a solution for a vessel schedule design problem that does not care about the emissions, where everything is just optimized such that total costs are minimized, and for a green version of the scheduling problem, where the emissions are bounded to certain maximum values, and for this reason we have a solution from this that is somewhat more environmentally friendly. Slide 10 shows us some results for both these solutions. The vessel schedule design problem that does not care about the environment gives us some results that are expressed here by the red bars. The green vessel schedule design problem, where emissions are bounded in the planning, leads to a solution that is expressed by the blue bars. We see that total cost increase for the green version of the problem. This is quite expected, because if we restrict the emissions that are allowed for these ships, we might have to go at lower speed, which in turn means that we probably have to deploy more ships to meet our service frequency and the time windows at the ports. The higher operating cost of the vessel fleets shows us that there are more ships deployed in the green vessel schedule design problem just to meet the schedule from the reduced speeds. We can see that the bunker cost decreased significantly, which corresponds to a saving in fuel and emissions. In the end, total costs are higher for the green version of this problem, and it is up to the ship operator to check out whether they accept these higher costs in order to achieve a more green transportation or not. The final slide gives you again the list of references and 2 ideas of things that you could think about. These read as follows. In the beginning of the COVID-19 pandemic, some container liner services used slow steaming, which was shown on slide 6, to reduce fuel cost and transport capacity. What effects did this have on their service schedules? And the second thing is, the maritime industry has to use cleaner fuels in the future. For example, liquefied natural gas, so-called LNG, or hydrogen-based fuels. What are the challenges for the maritime industry to switch to such other types of fuels? Thank you for your attention.